All right, the following is an instructional video on how to use the Civil Infrastructure Vision program in its bridge calibration format. So this is for measuring deformations on bridges. My name is Wasim Ganoum, and I'll be presenting this to you basic theory and also how to use the actual system. The system, I remind you, has been developed at UTSA by myself and my research group. So the outline here is I'll start first talking about the capabilities of the system, all the hardware and software components of it. I'll talk a bit about the digital image correlation principles that lead to the system's functionality. I'll talk about some accuracy validations that we've done both in the lab and in the field on the system. And then I will move into how do you conduct a live test. So how do you measure deformations on a bridge live? And then I'll talk about how to post-process either the images or the data that you collected from a live test. So we can reprocess either the images, and you can do a bunch of calculations such as interpolation between the data that is lost intermittently, smoothing the data, and calculating values from data. So the capabilities. So the system basically measures the three-dimensional movement of any target in space, in three-dimensional space. It uses two high-resolution, low-noise cameras. These are monochrome cameras also. They are not color because monochrome cameras actually have better resolution for this application. And uses DIC, digital image correlation algorithms, and triangulation principles to find those targets in space. So the output, the main output of the system is the 3D spatial coordinates of targets that are selected by the user on the structure they're considering. In the bridge edition, it is calibrated to a relatively large measurement volume, so this system can work from very small scales at the material scale levels, so small coupons, and can be used at very large scales also at the bridge, a complete bridge level. So this particular bridge edition is calibrated for a distance range of 40 to 110 feet from the cameras and a horizontal field of view that comes out of it between 17 and 47 feet. So at 40-foot distance, if your structure of interest is 40 feet away from the cameras, you have 17 feet horizontally of width that you can see. And if you go all the way up to 110 feet distance from the camera, you can see up to 47 feet wide based on the lens configuration. The measurement accuracy of the system is on the order of a hundredth or a few hundredth of an inch over the full measurement volume. Now, that's very important to note here that system accuracy is achieved for small relative movements only. So this is you're monitoring a target that is moving in space, half an inch, 1 inch, maybe 2 inches. So small relative movements of those targets is where we can achieve this kind of hundredth of an inch level of accuracy. The system is not intended to deliver high accuracy for very large movements that are greater than a few inches. So if you have something that moves across to your field of view several feet, you will not get the 1/100th of an inch or so, or a few hundredth of an inch accuracy that the system is made for. So what are the hardware and software components of the CIV? First and foremost is the two high-resolution cameras. So these are digital image cameras. They are fixed on an aluminum bar, as you can see in the picture here, and they are fixed at 30 inches on center spacing. The relative positioning of the cameras is essential to the accuracy of the system and to the measurements. Because it uses triangulation, the system knows where the cameras are with respect to each other and uses that information to figure out where everything else is in space. That distance is critical. So it's important never to bump the cameras or move them. Otherwise, a recalibration has to be performed. To minimize that risk, we added these two aluminum boxes around them. The boxes and the cameras are independent. They are not touching each other at all. So if the box get bumped, the cameras do not get bumped as well. So we try to make a separation. However, nothing's perfect. So if the cameras roll down the hill, you will most likely need to check the calibration to make sure the cameras have not moved with respect to each other. Now, so these are the cameras, they're sitting on the bars. The other piece, well, you need a tripod. If you're in the field, a surveying tripod is the best one to have, or something that's very stiff, so not your regular camera tripods are typically very flexible. This tripod really helps minimize any vibrations from wind and such. Next component is the laptop computer. So for the field, we provide a laptop computer and also a PCIe card expansion box, which is shown here in the picture. The system needs this box because typically the Ethernet ports on the laptops are not fast enough to be able to handle the bandwidth of the cameras. And typically laptops only come in with one Ethernet port. So this PCIe extension box has a specialized card that is a data acquisition card where the cameras can plug into it. And the laptop provided here has also dual hard drives. So a C drive and a D drive. The C drive is an SSD drive, where the D drive is a standard spinning drive. The C drive is recommended to be used for saving images during a live test to avoid any image queuing. So these cameras will max out 2 gig E connections going into the laptop, so the hard drive has to keep up. So that is why it's highly recommended to save images during a test on the SSD drive. Then the D drive can. Next are the high contrast physical targets. So these are made of foam core aluminum. We provide 3 different sizes, which are 4 by 4 inches, 7 by 7 inches, and 10 by 10 inches. So as if a target is close or 40 feet away from the cameras, you'll need a 4 by 4 inch, but as you go farther up to 110 feet, you will go up to the 10 by 10 inch cameras so that they have a reasonable size in the image. 40 high contrast targets are provided in each of the sizes, and they're all attached to aluminum angles, so it gives you versatility of how to attach them to the structure. So where do you want to use these? Well, wherever there's very limited contrasting features, so you have a surface that's very, very clean, which is extremely rare in older bridges. But should this ever happen, that's one place you can put these so that the system can find the targets more reliably. Or where you want to have just a reference point. So maybe you want to have the targets lined up at midspan, so you always know where your midspan is. So they can also be used as reference targets. Also provided is double-sided tape, so that double-sided tape is used to both tape the targets to the angles and to tape, you put them on the angles or on the target and glue them, attach them onto a bridge section or any structure that you want to monitor. So these double-sided tape will stick to things and is easily knocked off. So you can, at the end of the test, just come in and knock off the targets and they will not stay there very long. So strong enough to keep them in place, but not so strong that it makes it very hard to take them off or have them peel off paint with them. Also for tall bridges, such as the picture you see here, you may not want to put any scaffolding or ladders or anything like that. We're providing a 30-foot expansion rod where you kind of glue lightly the target onto the expansion rod and then stick it up on the bridge and then come in with the rod again and knock it off at the end of the test. It's very convenient, saves a lot of trouble in terms of safety, rigging, and all that stuff when you have higher bridges. So hardware that is not supplied that is necessary is a portable power source. So we do not provide a portable power source for the field. So it is your responsibility to bring one out. It can be a generator or battery pack. Just make sure that the power supply is not one of those square kind of jagged power alternating power supplies. It provides a complete sinusoidal shape, not the step functions. The cameras and the will use very, very little power, so you don't need a very big power supply for them. Another thing that is very useful is a distance measuring device, such as a tape measure or laser measuring device. That is useful when you're setting up, so you know how far you are from your target, how far you are from your bridge, so you are always within the measurement volume that you're considering. Tape measures work. These laser distance finders are very, very convenient, so you don't have to kind of run the tape over. So it's highly advised to keep one of these with you when running tests. Optional hardware are lights. So lighting in some cases may be necessary. Sometimes you have very high contrasts in a day, so it's a very bright sunny day, but you're trying to measure on the underside of a long dark bridge under a culvert or something, so you're really in a dark. So you have these big contrasts between light and dark that make it difficult to make measurements or to actually see your targets and the images. So in these cases, artificial lighting is recommended. Any lights will work really. However, if you're using lights like halogen lights that produce a lot of heat, it is advised that you do not put them right under the cameras where the heat that rises, you can see kind of the air ripples from the heat will actually add noise to your data. The measurement is so refined that even ripples in the air like that, we've seen it in experiments where it will add noise to your data. So if you're using lights that do generate a lot of heat, it's best to put them kind of left and right of the cameras, so they're not the heat that's rising is not in your line of sight. Or LED lights work really well. They never generate heat, so those can be put anywhere. So hardware connectivity, how do you connect things? Fairly straightforward, not a lot of connections to be done. The laptop is a regular laptop, has its own power supply if you need to plug it in, or it has its own battery if your test is short enough, it can run off its own battery. Then you have the PCIe expansion box. It has its own power supply, so you need to plug it into its own power supply, and it has a card in the back that has two Ethernet ports. So these are like the ports that you use for kind of plugging your computer into internet. And it has two of them. You just plug the cameras, the Ethernet cables that are pre-connected to your cameras into that PCIe box, and you plug it into its power supply. Now for the cameras, they also have a power supply that is already pre-connected to the cameras. You will connect those power supplies to the power, to any alternating 110 volt power supply. And as I mentioned, the Ethernet cables that are already pre-connected to the cameras and bolted to the box, so they cannot be pulled out accidentally, will go into that PCIe box. So this is pretty much it for connectivity. As a note, if always verify that the Ethernet cables are clean and don't have any damage. So if you start damaging them, running over them, or they get walked on and things like that, they can start malfunctioning and not sending information correctly. So if you need to replace these cables, category 5E is the minimum or higher, so 6 or 7. Any higher category than 5E is okay, and you can only use a maximum of 100 feet long cables. If you do replace them, you'll have to open up the top of the box, go in there, unplug it, and change it. Please be very, very careful not to shift the position of the cameras if you ever have to do that. And always use identical cables, so same length and same type for both cameras. So if you have to replace one cable for one camera, you should replace both cables for the two cameras and have them be the same length and the same type. This is because there's latency in the signals. If you have a very long cable and a very short cable, the signal to one camera will get there faster than the signal to the other camera. So it's important that you use the same cables. Also, I'll remind you, please do not use the computer's Ethernet port to plug the cameras in. Always go through the PCIe box, the Ethernet port on the computer is not fast enough, and there's only anyway, in any case, there's only one of them, and it's not fast enough for the data throughput of the cameras. Onto the software. So really one executable file has been compiled into one executable file, and it's a shortcut of it is provided on the desktop. So when you open the laptop, it'll be there. It's a civbridge.exe. So this is the file you'll need to run to get started. The software has two main modules: a live test module where you'll be running a live test, and we'll talk about it a little bit later, and a post-processing module that has all these extra processing functionalities. Now the system is delivered pre-calibrated, so the system needs calibration files to operate, and these files are provided, and they will be provided on the desktop as well in a folder, and you will load these calibration files every time you run a live test or post-process the images. We also provide instruction manuals. So this presentation or this video here, some is really going over through the user manual. So the user manual has all the information I'm providing here in more detail. So that user manual will be provided, and it's a PDF file and will be put on the desktop as well for reference. We're also providing a calibration validation manual. So this provides more detail on the validation manual that I will be describing a little bit later. This is a validation method just is provided to the user so that you can verify your calibration every so often, so that you make sure that your instrument is not drifting, or some accidental bumping or changing of the camera positions has happened. So I'll talk about this, and there's a manual that goes along with it to kind of show you how to test the calibration to make sure it's still correct to your tolerances. So let's talk about digital image correlation principles, so you understand a little bit of how the system works, so you have a better sense of what to do and what not to do, and what is a better situation than another when you're trying to conduct. So how do we go from images to 3D location and space of targets? So first step is we use the DIC algorithms that find target in each camera image. So you'll have a left camera image and a right camera image, and the digital image correlation algorithms will find a target in both of them, the same one. What a target is not what you think. It's not a physical object in the software. It's nothing more than a sub-image that is cropped out of the full image. So you see all those little targets shown here in green. So what the software does, it takes that little square, crops up the image, the picture out, that little square picture out of it, and that is a target to the system. So you can select it on anything you want, and that is what the system will find. This image in the left camera image and will find it in the right camera image, and that's what the DIC, the digital image correlation algorithms, do. It finds those to very high accuracy, within subpixel accuracy in the images. Now it's important for the system to work that the target shape and the looks of it don't change over your test. What the system is doing is then in each subsequent image is trying to find that exact same target. So the one that it cropped out, that sub image, is trying to find it in all of the subsequent images of the test, and then it finds how it moves around within the image. But if the target changes shape or size, or maybe you get a big crack going through it, or some water comes onto it and it looks different, then the system will not be able to find it, or will find it less reliably. So it's important when you pick your targets that you pick them such that they do not change how they look or how they appear over the experiment. Now, once you have the pixel coordinate of a target here, and this figure here is showing the projection from the camera, the line of sight over to a certain target, and you have the pixel coordinates of that target also on the other camera, you can triangulate the location of an object in three-dimensional space, and that is the triangulation process. That's what takes it from the pixel coordinates on each camera and gives you the three-dimensional coordinates. Now that is why it is very important when we calibrate the system, it knows exactly where these two cameras are with respect to each other, such that it can project the two rays and find the location of a target. If the cameras move relative to each other, then the calibration will be off and the numbers will be off as well. So a bit about measurement accuracy and noise. The accuracy of the system, as I'm going to show later, is on the order of 1/100 of an inch, 1 to 2, 3, depending on where you're at, 1/100 of an inch. Now the accuracy is certainly better in the XY plane of the camera sensors. So if the movement is kind of in line in the same plane as the camera sensor, called the XY plane, then the accuracy is much better. Now, it is not as good in the Z direction, so if you're going away or towards the cameras in that direction, that is not as good. Now, also accuracy is typically better as you get closer to the cameras, so at 40 feet, you will have better numbers than at 110 feet, so the farther you go. What I advise here is you try to set up your cameras such as the bulk of the movement that you're measuring is in the XY plane. So let's say you're looking at a bridge, you want to be looking at a bridge kind of level and horizontal with it and straight at it, so that the movement up and down is in the plane of the sensors of the camera. What you don't want to do is go right under a bridge and look straight up at it. So the camera is looking straight up. Now the bridge, as it goes down and up, that movement is essentially in the Z direction, so in the outer plane direction, and you'll get higher noise and slightly worse off accuracy. And that's what this figure here shows when we did an experiment at 30 feet with a different calibration. You'll see the noise levels are pretty low in the X and Y direction, but in the Z direction, the noise can be quite a bit larger. Now, noise is not the same thing as accuracy. Accuracy, we measure it according to NIST certified gauge blocks. So it's actually how far are you from an actual reference measurement. Noise is just what you see here. It's kind of that oscillation about a certain reading. The higher the noise, the worse you are off, because you cannot distinguish a very faint signal out of a big noise. So if your noise is on the order of several hundredth of an inch, then you won't be able to pick up a movement of 1/100th of an inch. So that's why you want to be mostly in the XY direction, where not only the accuracy is better, but the noise level is lower, so you can pick up even the smaller deformations or movement thresholds. A bit about target quality considerations. So as I mentioned, targets are nothing more than cropped up smaller images from the main image. And the target quality really depends on the amount of contrasting features it contains. So you can have something that's very smooth like this. This is not a very good target, or something like a steel section that has no features at all. And then you have things like this that has very good, a lot of features and a lot of contrast. So in general, what you get is if you have more features, you have better tracking and lower noise. So the system will not lose the target and track it much more reliably. And if you have higher contrasts, so the color contrasts are bigger, so you have black over white, which is the extreme case of contrast, you'll get better tracking and lower noise. Now, however, this is where the CIV system is really good. We spend a lot of time developing the algorithms and looking at which algorithms work better in what situations. And the system is fairly robust in terms of target quality. So it needs minimal features to track a target reliably. So any surface with just the slightest kind of feature, like one line, will be enough for it to track it. So it's very rare, especially in older bridges, to find a surface that has absolutely no features at all. In that case, you may have a bit of an issue, but in most cases, you'll have dirt, you'll have some rust, you'll have some spalling, you'll have something on it where the system can catch on. Now, target size is important, and target size is not the physical dimension I'm talking about the pixel dimension, so that sub-image you're going to crop. We highly recommend you don't go below 60 by 60 pixels. So that's when noise starts picking up quite a bit. That's kind of the minimal recommended target size, and the system allows you the flexibility of selecting different size targets. Our recommended target size is about 100 by 100 pixels, which is the default when you run the program. We tried bigger targets, and beyond 100 pixels, you start going up to 120, 150. You're not really gaining much in terms of quality of measurement. And you start risking also, you have more chance of having cracks running through the target or other things running through your target because it gets bigger and bigger. So a recommended size is 100 by 100. You can go lower. Sometimes you're kind of crammed and you're trying to pick something that's small in between two other items. But try not to go below 60 by 60. The software will let you go wherever you want. We don't have any cap on it. But if you start going below 60 by 60, you'll start seeing quite a bit of noise in your data. Lighting considerations. So the target location depends on the DIC perception of features in the target. So how the image sees the target, how the system sees a target from the picture is what determines its location. If you have very sudden or big lighting changes, they can generate fictitious movement of targets because how they are perceived by the system can change a little bit. And so here again, we put quite a bit of time looking at robust algorithms with respect to light changes, and we ran a test where we took 3 targets, concrete, steel, and a high contrast kind of printed target, and we put them in bright daylight, as you see here, and then we moved from bright daylight to very strong shadow, like straight up shade, and we get this plot here. So here we're going from bright sun, just sun, and this point is kind of the average location here, averaging out that noise. Then we take it into shade, and then we put it back into sun. You'll notice very, very little, if any, movement within kind of the noise levels. So the system is quite robust, and especially in the XY plane. Now in the Z plane, we kind of see that shifting, and you'll see this here. But this is kind of an extreme case. You're going from direct sunlight to full shade, which is usually rare to kind of see out in the field. In summary here, even though the algorithms are pretty good here and they do a decent job at not introducing those fictitious movements due to light changes, it is best to avoid light variations during tests. So try to test while the sun is up, or not where clouds are moving in and out, if you have the luxury. If you do not have that luxury and you do expect a lot of lighting changes, then we advise that you use the high contrast physical targets. They're black on white. That high contrast black on white will minimize the light shift, and these values here are for high contrast physical targets. Vibration considerations. Any vibration of the cameras or the bridge that you're monitoring will induce noise in the data, obviously. So it's best to try and minimize those vibrations. For the cameras, use a stiff tripod. We're providing a survey tripod for that reason. Locate preferably not on a vibrating surface. So if you put your cameras on another bridge or some vibrating ground, you will see more noise in your data. And avoid high wind areas. Try to shelter your cameras. If it's a very, very windy day, maybe you don't want to test on that day, so you don't get that extra wind vibration. Remember, you're measuring things down to very, very small numbers. So even kind of the smallest vibration will get picked up. But on any average day, unless it's really, really gusting, the system should work just fine. For the bridges, I mean, you can't do much to the bridge other than try not to test on a very windy day if you can. All right, so now on to accuracy validation. So the CIV system is only as accurate as its calibration, so that's very, very important, something to keep in mind. We've done field measurement field validation, and we've done lab validation. So I'm going to start talking about the gauge block verification method. This method is provided as part of the system so that you can verify your accuracy over time and make sure that your calibration is still operational. So, as with any measurement instrument, drift can occur over time. And this is something that's also happens with wire pods, linear potentiometers. They all drift and they all have to be recalibrated over time. So this is a natural process. Also, you may accidentally bump the cameras and shift things, so you may want to kind of test it to go, well, I wonder if this did something to it. Let me see if the accuracy is still where I want it to be. So that method is provided to you and is explained in the calibration validation manual. Now also we provide with this the gauge block measurement device that I'll talk about later, and a spreadsheet if you want to use it to help you kind of calculate all those accuracy numbers automatically. Should the calibration accuracy come into question, please contact UTSA for a recalibration. We're happy to work with you to get that done. All right, so the supplied gauge block device looks something like this. The concept is quite simple. So there's 3 targets here, 1, 2, and 3 that create the reference axis. So you select these as the reference axis. And the middle target here is on a spring loaded on a rail. So what you'll do is you'll raise this target here, put a gauge block down here. There's a surface to put the gauge block there, and you lower it down. Now, how much this center target moves, it should be the exact amount of the gauge block length, and these gauge block lengths are NIST certified, so they are, the length of these gauge blocks to a very, very good small tolerance. And so you compare the movement of that target that the system gives you with the gauge block number, and you can figure out the error. Now, when we deliver the system factory calibration, we provide accuracy measures using this gauge block over the entire measurement volume, and I'll show what that looks like. So these sheets will be delivered, but for you to rerun it, this is basically the process. You just kind of put the gauge block, move the target, and see how much it moves. So when we do a full measurement volume check, we look at distances between 40 and 110 feet. We typically do 3 of them, 40 kind of the beginning, the middle, and kind of the end of the measurement volume. We also look at the field of view, the image that you're seeing. We break it down into 9 quadrants, so kind of 3, like a matrix of 3 vertical, 3 horizontal, and we also measure the accuracy in each of these 9 quadrants. And we also measure it in the y-axis, or kind of the xy plane, and the z-plane, which is the outer plane direction. So if you take all these 3 distances, 9 quadrants, 2 directions, you actually get 54 different measurements that we put together to give a accuracy measurement of the entire volume. What you need is the gauge blocks. We supply a couple of these also for the application, and the gauge block testing device, which is also supplied. For measuring in the y direction, you'll put the gauge block this way, and this target will go up and down in that direction. To do it in the z direction, you can lay down the gauge block device, and now this target is attached in this direction, and you move it in and out of the paper or the screen, if you can imagine. That will move it out in the z direction, and that's how you measure the z direction accuracy. Here's what it looks like as you're running the test, showing the gauge block in the middle left quadrant. So this is the middle left quadrant, and we will do this by moving it all around. Now, you may not want to move the actual gauge block. It becomes difficult, especially at 110 feet and moving it up and down. What we typically do is keep the gauge block at the distance that we want, and we'll just kind of rotate the cameras on the tripod so that we get the device in whatever quadrant we're looking for. So kind of step by step. So first set up your gauge block and somewhere at the distance you want. Preferably do this indoors so you don't have wind vibrations and other things going on and lighting variations. You put the gauge block in the desired orientation. So for the y-axis or z-axis, you lay it down flat. You start a new live test, and I will explain later how to actually run through a live test. But you start a new live test and follow the procedure as explained in the validation manual. You select the reference axis system. So core targets 0, 1, and 2 give you the x and y coordinate system relative to the gauge block system. And then you'll track the target number 3. We highly advise that you use 100 by 100 pixel size to do this. And when you're putting the gauge block, so you track the location of these targets for maybe 30 or 40 images. You pause the system, you come in, you put a gauge block in there, and then you monitor the location of these targets again for another 30 or 40 images. And the difference between the movement of that target will give you the accuracy comparison. Now, it's important not to move the device when you put the gauge block, so you don't shift it in positions because that can affect the readings as well. And so if you want to do the full measurement volume, you repeat this for 9 quadrants, 2 directions. Now you can also just do this as a spot check. So this here I'm explaining how to do it for the entire measurement volume, all the quadrants and everything. But you may just want to do this, a couple of distances, a couple of locations, just, like quick spot check if something, just to see if something happened to your system. So you bumped it or something, or a quicker, faster check. It can be done relatively quickly if you're just trying to check a couple of measures. In the Excel sheet we provide, I mentioned, is kind of helps you calculate all these accuracy systems. So here's a sample calculation sheet for the y direction at a certain distance, and what you have all the 9 quadrants. So top left, middle left, bottom left, and so all these quadrants here. In this case, we did it with 2 gauge blocks, so a gauge block that is 3/4 of an inch long and a gauge block that is 2 inches long. And we find the location of that center target and the y coordinate of that center target here. And then we get the error between what is the movement. So we start off when you have no gauge block, it is 4.4475 inches relative to that reference axis that you selected in the y direction. When we put this gauge block in, it's at this y coordinate, and when we put this gauge block in, it's at there. And so looking at how much it moved compared to the actual dimension of the gauge block, we get the error. We average these errors in the absolute, so not in the absolute of these errors for these 2 gauge blocks, and we get that number for that quadrant, that distance, in that direction. Now, for the factory calibration, we do provide 6 of these sheets. So you have 3 distances and 3 and 2 orientations, Y and Z. So you get 6 of these sheets that cover the entire measurement volume. We provide these sheets with all of the accuracy measurements that we have done for them. Now, as you notice, the error is on the order of a 100th of an inch. It could be in some places higher, maybe 2 or 300th of an inch, but that is the order of magnitude of the error that you'll see in these sheets. The errors, as I mentioned, tends to be smaller in the center of the field of view as opposed to the edges. So measurements in the middle of your screen is better than kind of in the corners, and the errors tend to be smaller at shorter measurement distances. Now talking about a field validation, so we also took the system out where the University of Texas A&M was running a full load test on this steel continuous multi-girder bridge system. They were out there and they put a bunch of scaffolding and they put a bunch of traditional instruments, so you can't see them in the pictures, but there's wires going down, so they have wire pods and potentiometers attached to this bridge here for monitoring, and they brought in a truck that is weight truck over the bridge. We came in also and tagged along to kind of verify our system. We put up our high contrast targets, you see them there, and measured and compared to their numbers. So it took us, when all said and done, is the whole setup for the camera system is about 2 hours long. Could be a bit longer, could be a bit shorter, depending on how complex your location is. And we also, and that is including attaching those high contrast targets using this pole up there. And that's kind of a picture from the bridge of the setup. We're about 100 feet away from the bridge in this particular instance and right at the edge of that creek. So looking at truck path 1, so the truck was closer to us, and the girders are girders. 1 is the one farthest away from one, girder 1, 2, 3, and 4, 4 being closest. And so when the truck came in and stopped at mid-span there, we measured the mid-span deflections of those 4 girders, and we get about 0.7 inches for the girder closest to us, 0.56 inches the second girder, 0.35, and about 500th of an inch for the girder that is farthest away over there. Notice that you are picking up even a 500th of an inch movement is being picked up by the system. And you'll also notice a couple of other things. One is that the noise increases as the distance increases. That is very perceptible here. To counteract, actually, before I move on, to counteract this effect, in this experiment, we were forced to use smaller target sizes. We're really far out there because we only had same size high contrast targets. And so we were starting to butt up against that 60 by 60 pixel limit over there, where we could select something that's more closer to 100 by 100 pixels over here. So here's not only the distance that's increasing the noise, but also having to select a smaller target size, and you can see the difference. So if we were able to do 100 by 100 pixels all the way out there, we would have gotten better noise than this. Now comparing the vertical deflection for those 4 girders, our numbers are here that are shown in this figure here, and the A&M team's numbers are here. Our differences between them are on the order of a few hundredth of an inch, which I think is really great because we are not measuring the exact same point, so they're measuring something a little bit to the right of us. And even traditional instruments also have error or calibration issues. So no instrument is really perfect. And so once we see that we are within a few hundredth of an inch from each other, this kind of shows us that our system works as well as those traditional instruments. Now the advantage is that we set up in 2 hours. It took them about 2.5 days to put all that scaffolding up and attach all these instruments on that bridge. So speed is where the CIV system really wins out. Another place where we went out also is that even after 2 days or so of installing instruments, they were only measuring at certain locations. Whereas now, because we're using the camera system, anything that's in this field of view can be measured. We can select the target here, we can select the target on the concrete, we can select the target here on the pier. So anywhere you want, you can measure. So that is also another very big advantage of the system. Looking at truck path 2, so now the truck is farther away from us, so things get reversed. So the girder that's farthest away from us deflects about 0.7 inches, and the girder closest to us about 0.06 inches. Again, we compare with the Texas A&M traditional instruments, and also we are within very small numbers of them. Other things, here's just illustrating the crawl test. So the truck was going down about 5 miles an hour over that bridge, and we can see all the 4 girders because it's a continuous girder. So when the truck is on the span adjacent to the span we're monitoring, we see that the middle span, so this span that we're measuring, goes up actually, and then the girders go back down, and they go back down at different amounts as the truck goes over. Now, I've shown that in the lab we've measured the accuracy, and we're with kind of on the order of a hundredth of an inch or so, a few hundredth of an inch at most. And the entire measurement volume, we validated it over a bridge test also with traditional instruments, and we got some very good results there. So we have made every effort to provide accurate measurements. But of course, as with any instrument, drift can occur. The cameras can be bumped accidentally, and so should the calibration accuracy come into question, please contact us for recalibration. It's not a simple process to recalibrate over such a large measurement volume. And also, we do not assume any responsibility for the accuracy of measurements. So please verify them. Make sure whenever you're measuring, like any measuring device, always have your checks and balances. Just keep an eye for any data that may be off um, for any reason. All right, so now we're doing the live test. So I'm going to run you through step by step how to run a live test in these. When you open that executable file, the first thing you get is the main menu where you have just two options, two buttons. You have the live test and a post-processing button. And each of these will guide you through a series of screens. So the system is kind of straightforward. That way you go from one screen to the next screen to the next screen. So it is simpler to use. Now, at any point while using the program, when you're in any screen, you can exit the program by pressing this X button here on the top right of your screen, like any other program. But please be careful when you do that. This will exit you from the program, and any data that is not saved up to that point will not be, you will not see it. So please only press that X button to exit the program when you really want to exit the program. All right, so you click that live test button. The first screen that takes you to is the camera detection screen. You'll click on search for the cameras, and it will look for both the cameras. If it finds them, these two buttons turn lighter color, and it'll say, and then the next screen button here is activated, so you can move on to the next screen. If it does not find the cameras, you will not be able to move on to the next screen. Please check the connections between your cameras and the PCI box and the PCI box of the computer to make sure things are properly connected. Sometimes if there's something persistent, verify your cables. That could be an issue. Next, when it's found the screens, when it's found the cameras, the next screen is the project information screen where you enter the name of your project. So the first entry here is your project name and also the project folder name. Then you'll select the parent folder where that project folder will be created for you. So you select the parent folder, and within that parent folder, the system will create a new folder that is named after your project name here. Optionally, you can add GPS coordinates of your site or something like that. So if you want to remember where your site was, you can enter these. And for a pre-calibrated system, these numbers are just the camera information will be there automatically. Now, any information you enter here, GPS and things like that, will be reproduced in all of the output files. I'll show you where that is. So if you enter GPS and things like that, when the system produces the XYZ coordinate files, that information will be in there. So once you enter all this, you click the next screen and you enter the camera setup screen. So this is where you set up your camera parameters that you can change. First thing, you can do the region of interest. So if you don't want to see the entire bridge, the entire image, let's say your bridge is just very long and narrow and you have a bunch of sky on top and a lot of grass at the bottom and you really don't care too much about that. You can use this region of interest. It is in pixels. So for the cameras, it's about 4,000 some pixels by 6,000 pixels is kind of the image size. You can change these and recenter them. And what it does, it will crop up the images. So you will not see all of this. That helps for two things. One, the first thing it helps with is your image sizes become smaller. So you're not filling up your hard drive for no reason of images of sky. And the second thing, it'll allow you to run the test faster, so you can acquire images faster because you're not using the full image, so you can do faster frame rate during a test. So you can set this. You can also set the exposure time. So this is how long the light is allowed to enter onto the sensor. A longer exposure time will give you a brighter picture. Shorter exposure time will give you a darker picture. But if you get too long on the exposure time, then any vibration or movement during that exposure time will create kind of like a blur. If you look at photography of, let's say, sports events or things like that, when things are moving really fast, if you open the exposure for a long time, the object has moved quite a bit and you'll see a bit of blur. So we don't recommend you go above 15,000 microseconds. Anything below 50,000 microseconds means a faster exposure time is very good, will work, whatever works with you so that you're able to see the pictures and see the targets. Now, the system is far more sensitive than what you see on the screen. So we tend to aim for the fastest exposure time, so the smallest number here, that generates images that are not very dark. So the images are usually darker. We will go to darker than what you would like in regular photography. But as long as you can see the targets and pick the targets on the images, that works out. And the reason for it is the shorter the exposure time, the crisper the images get. So it's really a good thing to do. So once you set these two, it's kind of an iterative process. You turn on the cameras. When you turn on the cameras, you'll see the end result of your ROI and your exposure time. If you don't like it, it's just an iterative process. You turn off the cameras and you reset these parameters. And then you can turn on the cameras. So you cannot set these parameters while the camera is on. That's really what it is. So, and also this is a good place, a good screen for you to adjust your camera positioning. So right up till now, you just kind of put the cameras in a general location that you're happy with respect to your structure that you're monitoring. Here, you turn on the cameras, you see the images, and now you can do the finer adjustments of turning the cameras, orienting it to kind of see exactly what you want to do. So this is the screen where you do all of this. When you're happy with all your camera settings, you can save your camera settings, which will be the ROI and the exposure time. And this here kind of illustrates what happens. So when you turn on the cameras, these items here become shaded. You cannot use them. So you cannot change the settings while the cameras are on. So here you turn on the cameras, you move the cameras around if you want to move them. You see the images from the left camera and the right camera below, and adjust kind of iteratively until you get to what you want it to be. Then you click the next screen, you go on to load calibration files. So you will click on the load calibration files. You will navigate here. So the factory calibration is going to be put in this directory, the CIV drive CIV Bridge 2012 TxDOT factory calibration in this case. So that is the one. You will go there. You will load this folder. And when you folder, it will load all the calibration details. So this shows kind of the coverage of the calibration boards that have been used, the calibration quality over here, and the calibration name. Next, you'll move on to target selection. Now, this is optional. You technically can run a test without selecting any targets on the bridge, but it's highly recommended that you do at least select a few targets every test, just so at least you monitor that you are collecting data and that the system is actually finding the targets. Just to kind of make sure everything's operational. Also, it's nice to kind of pick a few targets, locations that are of interest, such as midspan of a bridge, so you can actually track a test as it's going along. So as I mentioned before, targets are just sub-images taken from the main images that the DIC algorithm will keep tracking in each subsequent image. The first step here in selecting targets is you'll click this Capture Image Pair button here. What that'll do is it'll capture image, right image, left image from the cameras, and these will become static. So when you're selecting targets, you're not selecting targets or images that are continuously being acquired. So it'll capture the images, these are fixed now, and you'll start selecting the targets in them. Second step is you'll select the target size. So the default is 100. And you have a search margin here that goes for the right camera. We'll talk about it a little bit later. It's best to keep the defaults unless you have a reason, or maybe your targets are too small, or you're trying to select something that's in a squeezed space, then you can go lower, but please do not go below 60 pixels. Next, what you'll do is you go to this screen here. So this is kind of a blow up of this left camera screen. And you can use the tabs that are here on the side of this image. You have the zoom button, the pan button, and the target selection button. So you can zoom in, you can pan until you get to where you want. Then you click this target selection button. It'll give you this kind of square. You'll move it around and you click it in the location you want, which is shown over here. Now, there's an optional here. You can also load pre-saved targets. So if you would like, if you're running the same thing where you're running the same test several times, and as long as your targets are exactly the same and they're in the same locations, you can just kind of reload them from a previous test. All right, so far what you've done is you selected this target here in the left camera image. The next step is to move the search margin, so this big box here, which has a size of 300 by 300 pixels, which is given over there. And you move it to the location where this target is in the right camera image. So remember that the left and right cameras are not going to see the exact same thing. So they will see different things. And because of the perspective. So things will be shifted in one image compared to the other. So this is why this is important. So you'll shift the search box, say, okay, this target is within this square here. And you click there, and if it finds it, you'll get another green square here saying that it has, indicating that it has found that target in the other camera image. So if the camera is found, you can click evaluate target, and it'll give you this estimate kind of defect map. So this kind of shows you the contrasting features in the target and also gives you a score. This score is allowed to be between 700 and 1000. 1000 means it's a perfect score. So the target is really, really very well captured in both images and very good target with high contrast. We highly recommend you select targets that have a match score of 900 and above. As you start going to lower match scores, 800 or even 700, then the system cannot find these targets very well. So these are targets that don't have a lot of contrast, and so you may start losing them during a test. So it's highly advisable to stay above 900. In most cases, you'll be above 950 without even trying. The system can find targets on pretty much any surface. So once you evaluate the target and look at the numbers, look at the match score, if you like it, you can add it. You click here to add target. It adds it down here, and this area here shows you all kind of the summary information for that target. And then you can repeat the same steps. So going back and clicking on a target on the left screen, putting the search margin over it, evaluating it, adding it, and so on. And so as you add targets, this here starts having all the increments. So this is all the target numbers. Let's say you selected 50 targets. If you click here, you'll have 0 to 49, which is 50 targets, and all the information is here. If you don't like a particular, so this is what you get here. If you don't like a particular target, you can go find this target number here, and also you notice here it also shows you what that target looks like. you can click on remove target and it will delete that target as well. So you also have that option, not just adding but also deleting targets. You can also delete all the targets and restart again if you want to. Your next step here is actually to select a user coordinate system. It is very useful to do so. Often your cameras are aiming at your structure at an angle or this Q, and just the camera coordinate system, which are the default, are not useful for you. So what you need to do is pick three targets. One is the center, the origin, which is the one here, origin. The X coordinate one, which is here shown as number 11. And the y-axis one, which is shown here as number 9. So you have the origin, target number 8, x-coordinate, x-axis, target 11, and y-axis, target 9. So what the system will do is take these three targets and will fit the best fit orthogonal x-y axis, and then the z will be out of plane. So this will give a reference axis that is orthogonal. So even though your targets will likely not be orthogonal, right, to each other, it will do the best fit orthogonal axis to those. And here now, if you want the vertical deflection, so then the y direction movement of all of your targets in your user coordinates become what you want to see here. So on to the next screen. You click the next screen, you get to the screen that gives you the reference images. So why it's important to have reference images? I brought this figure back here to show you kind of the noise. Remember, there's a lot of noise. So if your first image starts off, you take, maybe you can be maybe high on the data, you can be low on the data, you can be kind of anywhere within kind of that noise level. And so usually when we're calculating strains or relative movements or things like that, we're going to take the first kind of frame and say, okay, this is my 0 point, and I'm going to calculate numbers from it. But if it's kind of up or down or anything within kind of that noise, you're not going to get a really good zero benchmark or your zero deformation state. So what this does here is ask you for a number of reference images. We recommend 30, that's the default. Also the frame rate at which you'll take them. And then you click capture these images. What the system will do is it'll capture those 30 frames. Then it will find the XYZ coordinates of all the targets in those 30 frames, and then it will average those XYZ coordinates for all those targets over the 30 frames, and then it will use those numbers that it becomes the zero deformation. So this kind of evens out all that noise to give you a very good, smooth, level zero deformation state. Now, one thing I'll note here, these cameras are not very fast. They can go up to about, in full frame. So if you have the full image, you didn't crop anything, you can go up to 3.75 frames per second. I recommend usually just going 3 frames per second is a good place to be. And that frame rate will be used not only to acquire these 30 frames here for reference, but this will also be the frame rate that will be used for the tests. So please select it wisely here. Depending on how long your test is, you may want to go slower so you're not filling up your hard drive if you're not really trying to pick up things that are happening a little bit faster. So once you've done this, you click capture reference images. It'll pause. These number images here will increment until it takes the 30 images, and then you can move on to the next screen, which is setting up your plots. So on this plotting screen, you can set up to 5 plots, which are shown here, plot 1, 2, 3, 4, 5. And you can plot some basic information about your targets as the test is progression. So this is live plotting that is very useful for tracking your test. So the first thing you select is what coordinates do you want things to be plotted in. You can use, as I mentioned, user coordinates, the one that you've selected based on the reference targets, or you can use the left camera coordinate, which is the default. So the system will always produce left camera coordinate XYZ for the targets. But if you selected a user kind of reference axis, it will also produce those in those user coordinates. So you select the coordinate system you want to do this in. You then select the number of plots you want to have. In this case, we max it out at 5 to kind of illustrate what it looks like. If you select 5 plots here, it'll open up 5 different boxes. Each box is for a particular plot that you want. What you can plot are frame number, time, strain, and displacement for all the targets that you've selected. So, and on each plot, you can have multiple lines. You don't have to just have one line. So these are XY plots, and you can have several lines. So in this case, let's say you want the X data to be frame number, the Y data to be displacement, and in this case, we select the first line, which is line 0, to be the displacement between target 0 and target 0. If you use the same number, that will give you the relative displacement of the target with respect to itself or a 0 state. And you can also pick the line color and give it a name. Now, if you want to add another line, you increment this number here. The 0 goes up to 1. And then you can add another line, and so you can add as many lines, but on that particular plot, you're only plotting frame number versus displacement. On this plot, you're doing time versus displacement. Here we're doing frame number versus strain, or time versus strain, and then you can put as many lines as you want and set it up. Now, it's useful to do some plotting. Not to go, try to add too many plots, but you can do as many as you want. If you're wanting to compare 4 girders, the displacement of 4 girders, you can pick the 4 center targets along each girder and put them on the same plot, so you can actually be seeing the difference in the deflection of the girders as the test is moving. Now, once you're done setting plot, you'll click the next screen to get to the screen where you actually are going to run the test or start acquiring images. So your images and your data. When you click that next, it'll warn you that once you go there, you cannot go back. That's it. So you move forward, everything is set, and you're ready to do your test. And this here is the run test screen. When you get here, the cameras are turned off by default. Why we do this is sometimes you're sitting there and you have to get all this ready and set up, right? Everything ready, pick your targets and everything before you start your test. And sometimes you may be waiting a while before the loaded truck gets to go through, or the traffic control, or whatever have you. So what we do is we start you off on the screen with the cameras turned off, so that the cameras stay cool and while you wait. So when you're ready to start the test, you'll click this button to turn on the cameras. What that does, it turns on the cameras, but it does not start the data acquisition. Okay, so that just turns on the cameras. Now you see what you're seeing here. These 2 screens now light up and you can see what's going on, but data is not, you haven't started recording data. To do that, you will press this button. So here it looks like a pause button because test is paused. You'll click it and it will run. When it starts running, it'll start acquiring the images at the frame rate that you selected. Let's say 3 frames per second. It will do it quite well. It will do 3 frames per second exactly. And this image number will increment here. So this is how many images you're saving so far. Now you're actually saving data. Now you're actually saving the images, and the system is actually saving all the location of all these targets in XYZ space. You'll notice all these squares here are green. If the system loses a target during, sometimes it's just intermittent. Let's say you can lose it for a few frames and get it again. That square becomes red. So if these squares become red, you'll know that for these frames, the system has actually lost the target. And then if it comes back to green, that means the system has found those targets again. If you've picked your targets well, with good contrast, with a match score that's above 900, that should not really happen. But sometimes things happen, like a wire kind of goes in front of the target. Maybe the wind blows it, comes in, and then goes back out or comes back in. So you may lose targets intermittently this way. And kind of this is a good way to check. So when you're looking at these square colors, you'll know whether your targets are being tracked or not. So when you click the run button, this turns to green and says test is running. Data is being saved. Click to pause. You can pause anytime. If you are not saving to the SSD drive for any reason, you had to save on the regular drive and it's not keeping up, then the image queue will add up. So will start rising. This image queue shows you how many images are actually in the active memory of the computer, but not yet on the hard drive. So these are being buffered while the hard drive keeps up. If that queue starts getting very long, you should reconsider a few things. Either save on the SSD drive, which should solve this problem. You should not have any queues on an SSD drive. Or go back and run your test with a slower frame rate. So maybe 3 frames per second is too fast for the hard drive you're using. Bring it down. Or you can, if you have the luxury, you can pause. When you pause, all the images in the queue keep getting written to the hard drive. So this queue size will go down and you'll catch up, and then you can run it again, and then the queue size will go back over. So this is a feature just kind of show you what's going on, so you don't let too many images pile up in the buffer. And I mean, at a certain point, if you have too many and you don't have enough RAM memory, you will have a problem. But I mean, this feature is there, but please, if you always save on the SSD drive, you should never have a problem here. Now at the same time, your plots are being displayed, so you'll notice these tabs here. You have the tab that's images. So when you click on this, you'll actually see what's going on in the bridge and those targets with the green or red squares. But then you can also press the plots. So these are the plots that you have generated before, and you can see your data such as displacement versus time here, and it shows you everything. So you can see plots 1 through 5, and so you can cycle through them. You can see plot 1, plot 2, go back to the images, whatever you want to see here. As I mentioned, if you want to pause, so oftentimes you run the same test for the whole bridge load test. You'll run one test only. So when the truck is coming, you'll run it, you'll collect data, then you pause it while the truck backs up or goes around and comes back the other way. Then you can run it again. So you can pause and rerun. The image numbers will stop here, and the data will stop being saved. The images will stop until you press the button again to go in. At the end of all this, when you're done with all this, you press that big green button at the top that turns off the cameras and says this test is over. You can then exit the module, and that takes you back to the beginning, to the main menu of the program, or you can click the X to shut down. And that is the end of the live test. So now the good thing about the system is it will save images and will actually save the data, the XYZ coordinate data of the targets live as the thing is moving. So if for any reason the software crashes during a test, all the images and all the data, target data, up to that point are already saved. So you don't have to click save or anything like that. All that data is already saved. It is being saved live as the test goes. So that's kind of a precaution in case, and you never know, something can happen. Somebody can trip on a wire and disconnect the camera or so. So all the data is being saved up to whenever something happens or you shut down the program. Now here I'm showing you the folder structure that is generated. So under that parent folder, it creates a project folder. And in this case, the project folder is called Bridge Test. That's the project name and project folder you give in the second screen we talked about. And within that, all of this gets generated automatically. So let's talk about them one by one. So you have the targets. So all the targets are saved in the targets folder. So all those sub images of your targets, they are saved in this targets folder. The axis targets. So the three targets that generate your user axis, those are saved in the axis target folder. The reference images, those 30 images or so that you save up front that give you kind of the reference baseline, those images are saved here in the reference images folder. The calibration files are all saved here. So as a redundancy and a precaution, any calibration files you use, so when you load the calibration files, those calibration files get repeated and put back here. They're copied in the calibration results folder right here. This is a precaution so that you can, for any project that you do, you will know always exactly what calibration you have used for those results. So this is kind of a security, so you always know what calibrations you've used and they're always saved there. Next, if you save any camera settings, so that ROI and kind of the exposure time, those get saved in this folder here. And the test images, finally here, are saved here. So the test images, you have the right camera images and the left camera images. These are raw images that are uncompressed. They're in a bitmap, BMP format. They are quite sizable. And they are all placed over there. So these are uncompressed images. There is a file then that is project info data. So that's all that project info that you put in, like GPS and things like that, just gets saved in a kind of a text file here. And finally, last but not least, these are the CSV files. So these are just basic spreadsheet files. You can open them in any spreadsheet program. The basic xyz.csv file is the xyz coordinates of all the targets you've selected in the left camera coordinate system. That is the default. This file is always generated. And if you have selected, 3 targets to produce a reference axis, then the user coordinate XYZ file gets created. Usually that's of more interest because this is kind of lined up with your structure. This is your own coordinate system. Next step is post-processing of images. I'll start by how to reprocess existing images and we'll move on through these different modules. So back to the main menu. If you exit the module and you get here or you start the program again, you can select the post-processing function that allows you to do. So all of these functionalities are here. Within that post-processing, we're going to look at the first one, which is the reprocessing of existing images. Why would you want to reprocess existing images? Often in the field, you're rushed, lighting is poor, things are happening, and you may not have the time or the luxury to select as many targets as you want to track whatever you want. So in the field, you may select 10, 20 targets quickly, hastily, just kind of see what's going on. You run the test, everything goes, and then you can come back to the office, sit down, and now you say, okay, well, I really want to know the strain or the deformation between this point and that point. You've never picked it, so you can go back. So the system loses no information. So because the images are saved in a raw, uncompressed format, all the data is still there. So everything is still preserved in those images. So you can go back and reprocess those images exactly as if you were in that test the day of and do whatever you want with them. So the first step here is to load the project folder. So that's where your test images are. At the very least, your test folder must have reference images and test images for this to work. So it'll be looking for those 2 folders. If you do not have any reference images, it will have an error. So, but all the projects should have these folders. This is just to tell you that it is looking for these 2 folders. Do not change the folders or file names. So whatever the system generates automatically, even the CSV files, all those files, do not change them. Do not change the file names or anything. It will be looking for them. If you want to do something with them, please copy them somewhere else and work with them in another location. So once you load that project folder, it'll give you the project information that you've put in up front. It'll tell you how many test images were taken, how many reference images are there for that project, and So it loads up that information for you to see. Then you need to enter this information here. You need to name your data analysis folder. So this is the folder the system will create for you, and under it we'll put the new xyz.csv file. So all the new target locations, anything you're going to analyze here will get saved in that new folder. So you give it that folder name and you choose a parent directory. Now, I highly recommend that you use the main live test project folder directory as your parent directory. So the analysis folder goes kind of within your same project. And you can do as many analyses as you want. So you may have one live test and only one set of data of XYZ from that live test, but you can run 10, 20 post-processing image analyses, and each of them, so you can have like 20 folders with different analyses in them. And if you want to add any description here, you can add it, and that will be saved in the data files. Once you do this, same thing as before, you load the calibration files for the calibration, so same process. Here it looks very similar to the live test. Then you get to the target selection stage where you can either load targets and add to them, or then you can load the targets you used in the live test and add to them or change them. You don't want to load targets, you can select them all from scratch again, so it's exactly the same process as before. And then you get here. So here you can tell it to go back through the images and find those targets and all the successive images. You can either go from image, from the first image all the way to the last one, which is 598 for this particular test. Or you can also tell it, I just want to process in, these images from frame number 400 to 500. That's all I want in this processing. You select, so this is kind of the frame range that you need to process, and you click process the images. Now this may take some time depending how many images and targets you've selected. So the system will go load all these images and go through them one by one as if you were running a live test and get you the coordinates of the targets you've selected. Now, next I'm going to talk about the interpolation of existing data. This functionality is, and you get to it from here, from this menu under reprocessing, if you lose targets intermittently. So most often you will not lose targets if you selected them correctly, but sometimes for some targets you may lose them intermittently. So they'll be lost for like 3-4 frames, then come back again, then be found again, then be lost again. This could happen, let's say, if you have something blowing in front of it, or there's obstacles, or if the target quality is really poor. So you've picked something with a match score of less than 800. In that case, if you want to have kind of more clean plots with that target and things like that, you can run the interpolation function. This interpolation function really runs off of any of those CSV files, the XYZ CSV or the user coordinate CSV files. Your first step is to select whatever file you want to do the interpolation over. You open it, you click open, and then you click the frame limit over which you want to do interpolation. So let's say well, you can accept 10 frames. If it's lost for 10 frames, I will interpolate between those 10 frames, so you're actually filling in this data between it. But if this target is lost for 100 frames, don't interpolate. I mean, that's just then you're getting kind of weird fictitious data. Is too far of a window for you to interpolate. So this is your choice of how many frames you're comfortable letting it interpolate over, how many frames that are lost. So you select that and then you click interpolate. And what it'll do is it'll create a second file that is this name xyz1, and it'll call it xyz1 interpolate. So it'll take that file and kind of fill in the blanks where those targets have been lost by interpolation. And what the files look like is this. So here I'm showing you a sample file from a live test. Now you'll notice that the project name and a lot of information is repeated here, including the frame rate, the exposure time, all these things that you use for your test. The coordinate system targets are also listed here for your user coordinate systems, and other information is given here about your calibration. And when you take those reference images and those reference kind of zero baseline numbers are produced, this is the reference average line here. So what it'll show you is this is the XYZ coordinates of the targets when from those reference images. So this is your zero deformation state is given in this line. You'll notice that targets are numbered from 0 on, so x0, y0, z0, that's the coordinates of the first target you selected, x1, y1, z1 here, coordinates of the second one, and so on, every column. The columns after that is all the other targets. So every file looks like this, starts off like this, and you also have the date and the time, and the frame number over here. Now you'll notice here we selected a target that has a very poor match score, and so you have this not a number. NEN is for not a number. So you'll see it's found here, it's lost here, it's found here, it's lost here again. So after we run the interpolate function, it'll create another CSV file with all this information, same as the other one. But now it'll put the interpolation function, so the frame limit, and what is the source file that it's used. And you'll notice here that it's filled in a bunch of these nutty numbers by interpolation. Next is smoothing of data. Smooth your data, so any measurement has noise, and so if you want to have cleaner plots or look at things a little bit better, you're going to smooth out your data. We provide a smoothing function here, so you go in and click the smooth data. Same thing, it operates on the data files. No, it doesn't operate on any images or anything like that, so it takes whatever the CSV file you give it, but that CSV file has to be an original created by the software. Okay, so not because it's looking for certain features in the file. You click open. You can also select either a raw file from a processing of the images, or you can even pick the one that's been interpolated, so you can smooth the data after interpolation. So you can pick a data file, interpolate it, then take the interpolated data file and then smooth that one. So you open this file, you choose moving average or moving median. These are the two options we provide here. The number of samples to average, so this is your moving average over what window. So this is the window size here, is given at 7. And then you click smooth data. What it does, it takes this file, smoothes data, each column individually, so smoothes the X data, the Y data, the Z data for all the targets, and produces another CSV file with the same format, looking very similar to the first one, but now with the data. And that's kind of what it looks like. So we start with the file, the original file here, and when you run the smoothing function, it'll tell you, okay, it'll add the smoothing information, so smoothing average with a seven frame window. This is my file that is smooth, so my original file that is smooth. All the information here is the original information from the original file, and then it will run here and smooth the files. Now, if you want interpolation, or you're comfortable with interpolation, it's often best to run the interpolation before the smoothing. So you run the interpolation so it fills in any gaps, and then you come in and smooth it. So now you get nice, clean data to look at. Finally, I'm going to talk here about calculation from data. The plotting from process data looks very much like the plotting from the live test, so I'm not going to go into it. If you press the calculate from data function, it takes you here. So first things first is what data are you going to calculate from. So you pick any of the CSV files that you're interested in. Here again, the system is very flexible. You can pick the left camera coordinate file, the user coordinate file, the smoothed file, the interpolated, then smoothed file. So the combinations are endless. You can pick whatever of the files that the system has generated. You open it here, and here is the increment of how many calculations you want to make. So you can make as many calculations as you want. All it does is any calculation, it'll put it in a new data column. So start off with calculation 0 here. So everything starts with 0, and you select what calculation you want. You want the absolute distance between targets, you want the relative movement between targets, or you want strains. Then you select the direction. You want it to calculate strains or movements in the x direction, y or z, or xyz, which is kind of the vector coordinate, which is defined here. So it's just the vector coordinate, the vector direction between the targets you're selecting. And then you select the targets, target 1 and target 2. You calculate. And so this is all the information here. So you select the type of calculation you want, the direction, the 2 targets, and then you can increment this and keep adding more and more, as many calculations as you would like. When you then can select the new file name for the calculated data, so you select the file name for it and the directory where to put it, and you click the calculate and save. What it does, it generates a file that still has a bunch of the original project information up here. But now, instead of having XYZ, XYZ columns, each column has its individual name based on the calculation you're making. So this one is absolute distance between targets and the X direction, target 0 and target, I can't see the number here. So it will write very explicitly what that calculation was. So this is the distance between 2 targets in the X direction here. This is the absolute distance between targets in the Y direction here. This is relative movement between targets here, strain or another strain here. So it will calculate them, and as many as you create, it'll just keep creating a different column for it. Then you can take this data and plot it or do whatever you want with it. And that completes the presentation. If you have any questions, please email me. My email is wasim.kanoum@utsa.edu, and I'd like to thank all the team that has worked with me on this, my co-researchers, co-PI, Dr. Manuel Diaz at UTSA, and all the students listed here for their hard work getting this system to where it's at.